MBD is, of course, a method for making a decision about the magnitude of an effect, taking into account sampling uncertainty. But it's been criticised for lack of a theoretical basis for high error rates and for being misused. Well, the misuse has turned out to be minor. The error rates are acceptable when MBD is used properly, and it has two valid theoretical bases. In this 10-minute talk, I'm going to address this last point. The sample data can be used to construct a sampling distribution centered on the observed value of the effect, as shown here. The distribution is usually normal, a T or a Z distribution, and it represents the probability values of the effect that are compatible with the data and with the model used to derive the effect. There's no mention of the true value of the effect yet. The most likely values can be summarized as a compatibility interval, for example, a 95% CI, which encloses the most likely 95% of values, as shown here. The CI is bounded by the lower and upper compatibility limits, as shown there. And now I can mention the true value. It falls below the lower compatibility limit for 2.5% of samples. So the probability that the true effect is less than the lower 95% limit is 0.025. But MBD provides the probability that the true effect is harmful and trivial and beneficial. And so I have to introduce a threshold for harmful values of the effect. There we go, and there are harmful values. Now, what does the area of the sampling distribution falling in harmful values represent? In MBD, by analogy with the lower compatibility limit, it's the probability that the true effect is harmful. But the smallest harmful value is fixed, whereas the lower compatibility limit varies from sample to sample. So it turns out that to calculate the probability that the true effect is harmful, a prior probability distribution for the true effect is required. It represents just how big, in a negative and positive sense, the researcher believes the effect could be. It's reasonable to assume a normal distribution for the prior, and it can be represented by a compatibility or credibility interval, the range of values that the true effect that the researcher believes to be likely. So I'll now add trivial and beneficial values plus moderate and large thresholds. There we go. And I'm going to talk about a standardized mean effect so we can see the thresholds for small, moderate, and large. Here's a prior implying that large negative and positive effects are very unlikely. And here are data from a typical small study in our discipline. And the prior and the data combine to produce a posterior distribution. And it's the posterior distribution that can be used to calculate probabilities of harm, trivial, and benefit. This is a Bayesian analysis, and it can be performed with a spreadsheet that implements a method devised by Sander Greenland. The next slide shows the spreadsheet with this prior and data and with less informative priors. So here's the example. The prior is reasonably informative with a mean of 0 and compatibility limits of plus or minus 1.2, which is borderline large. The observed effect is 0.4, which is kind of arbitrary, but the important thing is the 90% CI of plus or minus 0.7, which is consistent with that small sample size. There we go. The posterior mean and the compatibility limits are shrunk to 0.31 and plus or minus 0.60. There we go. And if we add the smallest harmful and beneficial values, which are plus or minus 0.2, then we get the probability that the true effect is harmful, trivial, and beneficial. Fine, so here's the effect of a weakly informative prior and a minimally informative prior. And the bottom line is that there's only very slight shrinkage with a weakly informative prior and no shrinkage with a minimally informative prior. And of course, the probabilities are practically the same and the same as the MBD probabilities. That's with the minimally informative prior. So MBD has a valid Bayesian interpretation consistent with a minimally informative prior for all sample sizes and with a weakly informative prior for all but very small sizes. MBD is a valid frequentist method, and if we're going to understand frequentist methods, they involve hypothesis testing. The easiest way to understand hypothesis testing is with a compatibility interval. So let's test the hypothesis that the effect is harmful, and that's called a non-inferiority test. There you go, that's the region that represents the hypothesis. If the compatibility interval includes harmful values, some harmful values are compatible with the sample data and the model. There we go. The hypothesis of harm, therefore, cannot be rejected in this example with a 95% CI. The p-value for the test is the area of the sampling distribution in harmful values. Let's show that. And it's 0.066% of the area in this example. If a 95% compatibility interval is used, as here, the threshold value for the p-value is 0.025. And here the p-value is greater than that, so the hypothesis of harm is not rejected. The true effect could be harmful. With a 99% compatibility interval, the threshold p-value is 0.005, 0.5%. Here's an example of rejection with a 99% interval, with a p-value of 0.004. Right, so this p-value is, of course, the same as the MBD probability that the true effect is harmful. Now, in clinical MBD, an effect is considered for implementation if the true effect is most unlikely harmful. That is, the probability of harm is less than 0.5%. In other words, that p-value for the test is less than 0.005. So the requirement for most unlikely harmful in MBD is the same as rejection of the harmful hypothesis. Also in clinical MBD, an effect is considered for implementation if the true effect could be beneficial. This is equivalent to failure to reject a hypothesis. The hypothesis is a benefit and it's a non-superiority test. The threshold p-value is only 0.25. It's chosen so that a possibly beneficial effect is considered for implementation. Non-clinical MBD is used for decisions about effects that aren't implementable, such as the difference between females and males. The p-value thresholds for the hypothesis of substantial negative and substantial positive in this case are both 0.05. Rejection of substantial negative, for example, implies the true effect could not be, is very unlikely to be negative, and the 95% CI does not include substantial negative values. When the CI includes only trivial values, the effect is decisively trivial. You've rejected both substantial hypotheses, and that's called an equivalence test. And when the CI includes only substantial values, the effect is very likely or clearly substantial, positive or negative, depending which one it is. This is equivalent to rejecting a non-substantial hypothesis and in what's called an inferiority or superiority test or minimum effects test. In both forms of MBD, an unclear or indecisive outcome corresponds to failure to reject any hypothesis. So the Bayesian interpretation is the effect could be harmful and beneficial, or substantially negative and positive, non-clinical. And the frequentist interpretation is to say anything about an effect, you have to reject at least one hypothesis. So, in conclusion, here's an example of MBD in Bayesian and frequentist terms. The effect is possibly beneficial and most unlikely harmful. The hypothesis of benefit cannot be rejected, and the hypothesis of harm is rejected. So which of these gives researchers, practitioners, and end users a better sense of uncertainty in an effect? I prefer the Bayesian, but hypothesis testers should be satisfied with the Bayesian, knowing that it is equivalent to the frequentist. Thanks for your attention.